Okay, good afternoon, everybody. I hope everyone's having a wonderful day. So before we get started, I just want to remind you, remember your assignment 1 is coming up for its deadline. So just keep an eye on that. So other than that, I'm going to proceed to where we were last day. So last day, we started talking about this thing called the lower bound. So I want to first, before we start talking about that and some techniques for establishing these so-called lower bounds and what it's all about, I want to talk a little bit about different problems we could solve and think about some of the most efficient algorithms we know about, at least up to this point, for certain problems we've studied or looked at before. So the first one, remember we talked a little bit about this last time. So we talked about the search problem. Yeah, we could solve that in linear time. But remember, when I look at the search problem more generally, I don't have any additional information at my disposal. I'm just assuming it's a totally unordered array with no additional information. If I had more information, I might be able to establish maybe a better algorithm. For example, when the array is already sorted, then I can use something, for example, such as binary search, right? Now, we talked a little bit about this, and I want to mostly focus now on talking about sorting. So, because I kind of talk a little bit about sorting because it's going to be very relevant for what we're going to do later on. So, I want to remind ourselves of some sorting algorithms. Some you may have seen, some maybe not as much, but you may have heard of it. Other ones, a little bit more. I'm going to talk about some technical details that are interesting about them. So for sorting, we actually do have some really nice sorting algorithms for general cases where we have n comparable objects. So just as a reminder, a comparable means simply that if I give you a list of those objects, I can compare them such that one can come before another, or I could tell you that, for example, one comes after another. So for example, numbers have this property, strings have this property, many objects have this property. In fact, in programming languages, very often, if you ever want to define one of these comparable objects, it's something you can actually do. So many of the algorithms all the algorithms I presented here for all of these 3 problems, these are examples of algorithms that provide an upper bound on the complexity of solving them. So it means that think about the best known algorithm that most efficiently solves the problem. So these actually all are algorithms that solve these problems in terms of complexity, the fastest we know. I want to back up all of these statements today. So that's where lower bounds are going to come in. But before we get there, I want to talk about sorting a little bit. So you may have seen merge sort, for example, in 210. This runs in big theta n log n time in the worst case. And heap sort, you may have seen it, you may not have seen it. If not, we're going to definitely still talk about heap sort a little bit later on. It takes big theta of n log n time. But I'll defer the analyses for these ones a little later on, okay? I want to make also a remark about another algorithm you may have seen and probably spent a little bit of time with, possibly. There's another, you may have heard of these ones. There's another kind of like of the, I don't know, King Kahuna sorting algorithms. There's one that's kind of missing on my board here. Does anybody know which one I might be referring to? It starts with a Q. You may have been told it's a rather practical sorting algorithm. Yeah, quicksort. So now you might ask, Dan, there's sort of something a little bit different about quicksort compared to these other 2. For the first thing I want to point out is that if you take any general pivoting strategy for quicksort, there are some that are going to be good pivoting strategies, because just as a reminder, remember in quicksort, you have an array. So you have your array, and it will you break down the array based on a selection of a pivot. There's some other ones too, yes. Don't be forgetting about some other ones. But these are kind of like the more traditionally classic ones. I'm just pointing this out. So there's different ways you can select the so-called pivot. And the selection of this pivot will determine which parts of the array you examine recursively using quicksort. So ideally, we like it where the pivot is somewhere about the middle, so that it cleanly splits everything down the middle, right? But it's very real and possible for a lot of these pivoting strategies for it to be where the pivot is somewhere, sometimes at the beginning or sometimes at the end, causing it where you subdivide the array, your pivoting strategy ends up creating these really, really big chunks. In fact, so big that they're essentially just one element less than what you're currently examining. In those cases, you end up getting quadratic running times. So you get big O of n squared worst case time for quicksort, but on average, even in what I just described here, it runs in big O of n log n and average case time. So quicksort, although its worst case can be quite nasty, in practice, even if you give a distribution of instances, the pivoting strategies of most of these algorithms tend to work quite well on average. In fact, they match up with these ones. But quicksort is rather also simple to implement too. So that's a nice feature of quicksort. But you'll notice that this says worst case. It doesn't, right? It's not the same as these two. In these two, both of these are on worst case and on average case. So I want to talk a little bit about pivoting strategies with quicksort because there's different ways you can select this pivot that cause different algorithmic running times. So does everybody understand kind of like what I want to talk about with quicksort? Are there any kind of questions about what I mean by pivoting strategy? So just as a reminder, just remember, the pivot isn't a pivotal. I don't want to make this pun, but I will. So just please cringe with me later, okay? So if I have an array, I select a pivot, it's pivotal on the strategy of quicksort to pick a nice pivot. But the thing is, computing the pivot in a nice way might be a little bit tricky. So there's sometimes very simple and efficient pivoting strategies. Some of these you've seen probably in 210. There's a couple others I'm going to point out to you that you may not have seen. So I want to talk about some pivoting strategies that you could use. So I'm just going to mention depending pivoting strategies this may change. Most of them are not, though. Most of them are going to have this nice feature that I've just described here. So I'm going to talk over on that board about this. So let's move on over there. I'm just going to kind of walk my way on over this way. So let's walk on this way. And I'm going to stop talking. That's just too much. So the first pivoting strategy you may or may not have seen is where you just select the first or last element, sorry, the first or last position as the pivot. So if I have my partition of what I'm considering, I always look at the first or last position. This is a classic pivoting strategy. This one has big theta n squared worst case time. So you're not going to get much better when it comes to worst case for this pivoting strategy. Now, another one that's also well known and sometimes used is, sometimes it's called median of 3. So what I mean by the 3 is you just simply select the median of the first, middle, and last positions. Positions of a partition. Hence why it's called median of 3. The 3 positions are the first, middle, and last positions. You just take the median of those. And then that's what you're going to select for the pivot. So one part of quicksort that's really nice is that if you pick the pivot very efficiently and it doesn't dominate the running time, you usually can get away with doing a little bit more than just picking the first or last. Like this median calculation, I can get away with doing in constant time. So unfortunately, this doesn't get you much better when it comes to worst case complexity. So it's still big theta n squared worst case. Now, you might ask, okay, so what else do we have to do to make this better? Now, there's kind of two camps that I want to point out to you. Two, I would argue, very valuable camps to consider when you're thinking about sorting. So the first one I'm going to present to you is it's a little different of a result. It's going to involve randomization. And believe it or not, you may or may not have heard of this before, but if you use, so notice I have a first or a last, I have a median. Another strategy maybe we might use is a randomized pivot. So meaning you randomly select the pivot. So another strategy is the so-called, you can use a randomized pivot. Now, here's the interesting thing about selecting the randomized pivot. Now, it doesn't quite give you the guarantees that we're hoping for, but it gives us big theta, n log n, worst case, expected time. So you might ask, okay, well, then you talk about like worst case time. We've talked about that several times, right? But I've added this extra word in here. Now, does anybody have any suggestions maybe why we might not necessarily get a worst case time, but we'll get what we call a worst case expected time instead? Is there anything about what I just described by changing the pivoting strategy that might change how this algorithm's going to work? Because notice every time I compute a median, the median is highly dependent on the input itself. Selecting the first last position depends on the input. This, however, is a little different, right? Yeah, so now we're dealing with probabilities. And also, like correctly stated in the chat, there's nothing guaranteed about the selection of the pivot here. It's all entirely at the mercy of coin flips, or whatever randomized generator, or what we call pseudo-random generator, might give us. If you pick a very poor seed, it might not work very well. But my point is that when we talk about this randomized pivot, believe it or not, we can get it so that it behaves like n log n in the worst case, but this is on expectation, meaning it's very similar to thinking just about when we talk about average case over here, but instead of it thinking about where I take a distribution of the instances, instead it's actually implicit in the behavior of the algorithm. That's why it says expected, not average here either. So this is one thing I want you to be aware of, is that selecting a randomized pivot is actually quite a successful pivoting strategy. Why? Because you're taking advantage of the fact that we know that the distribution of the instances, quicksort tends to work quite well. So if you can make it so that pivot takes advantage of this fact, that's wonderful. However, like I said, this is expected. If you don't like seeing the word expected, it's saying worst case time on average. So meaning that you can still get it where it picks this really nasty pivot at the beginning or the end. Beginning or end. Where you end up having the partitioning splitting up in the way you don't want it to. That could still happen. But on expectation, it works quite well. So are there any questions about that? So I just wanted to point this one out to you. So this is one camp. Yeah. So you can first deny, yeah. So if you find yourself not set, that's actually a really good point. I wanted to bring this up, is that if you don't find the pivot being very satisfactory, you could recompute the pivot again, over and over again. But remember, like we would like the pivot to be something very quick for us to compute. So yeah, so that's one practical consideration you can make when you use a randomized pivoting strategy. Very good, very good. I like that. See, these are the things I like about when we kind of do things together. So we can talk about these things. So that's one camp, what you could do with, that's one of the camps. The other extreme, so this will get you basically n log n, but it's not truly worst case time. It's because it's dependent on how this pivot is getting picked. Here's the other side of this, is where you truly select the median pivot. So this is like the other extreme of this. So you can sometimes get these bad edge cases with the randomized pivot. Sometimes, yes. But actually, one thing I do want to point out is that picking a bad pivot is very unlikely with randomized pivoting. If you were to, now I don't have time to calculate it out for you, but if you were to try to calculate this out, you could effectively find out that selection of the pivot is in a bad spot is actually really low in occurrence. It's very, when I mean low, I mean like, you're not going to run into it very often. Just to stress this point. Now, on the other extreme of this, you might say, what do you mean by extreme? You could select truly the median spot that where you can get it so it cleanly divides into two equally sized partitions on your pivot. So this is sometimes called medians of median. Sorry, median of medians. I'm getting my tongue tied backwards. Median of medians. Or the other way you could talk about this is here's the crazy acronym. So if you ever find yourself looking for this algorithm, it's often referred to as Bloom, Floyd, Pratt, Rivest, Tarjan, or more appropriately abbreviated, BFPRT. So people will often refer to this approach as median of medians or the BFPRT algorithm. Now you might ask, Dan, what can you do and accomplish with this? Now, with certain data structures, you could achieve this in a certain way that allows you to obtain your big theta n log n worst case time. Now you might ask, Dan, how is that possible? It's because the selection of this median is done in big theta n time. If you actually pull out the analysis you may have done with quicksort, maybe in 210, you can actually see that if you were to introduce something like a pivoting strategy that takes this much time, it won't actually affect the overall time complexity. But the point is that there do exist ways to modify quicksort using a very specific pivoting strategy to allow it to take big theta n log n worst case time. But that's not true more generally. But the big point I want to get at is that for practical considerations, so this is why I said it's the other extreme, is that when you actually take and look at the analysis for this algorithm, so this pivoting strategy, so like the subroutine that makes this work, the constant that's in the analysis, you know how we sometimes have those constants that pop up in our analysis, right? The one that's in this one is rather big. So for practical considerations, you'll find that this constant may actually be not necessarily something that you want to deal with. So on one hand, you can quickly produce, using the randomized pivot approach, generally very good results. Versus this, it might take a little longer, but it's still going to take big theta n log n worst case time. But it will exactly compute the median position for the pivot. So that's why I mean by these being two extremes of each other. So this is actually one of those examples where I said, okay, sometimes those constants actually can really matter. But yeah, no, are there any questions about any of these? So I just want to give you kind of like a big picture look at what you could do with quicksort beyond what you may have seen in 210. But yeah, these are different pivoting strategies that exist, and different ones lead to different worst case time complexities. Most of them still give you the quadratic, But if you take things a little further and analyze them more carefully, you can actually get some of them actually giving you some nice guarantees on the running time. But yeah, you'll find quicksort in practice tends to work quite well. So, and there's been a lot of research, hence why there's so many of these pivoting strategies that exist. And they've existed since about the 50s. A lot of these pivoting strategies. Some of them are more recent, but yeah, some of the earliest ones, like the first last, I think that was at least the early 60s. So people have been studying quicksort for many years. I'm just trying to remember my dates correctly. I'm pretty sure that's the case. If not, I most certainly will issue a correction. Excellent. Are there any questions about this before I start talking about lower bounds? Excellent. So I just want to give you a flavor for kinds of algorithms that kind of meet where like our best known stuff usually is. Now there's other algorithms that do exist for solving these problems too. So many that I probably couldn't acknowledge all of them. Now the point is that we have an upper bound on the complexity for solving these problems. So these are based on characterized by the most efficient algorithms we have to solve those problems. So it tells us how efficiently we can solve the problem. So if somebody ever talks to you about the upper bound on solving a problem, they're referring to what's the efficiency or complexity for solving that problem. And they're thinking about the best known algorithm that exists. So the natural question is, once you're in that position about knowing what's our best known algorithms with our best complexities, are those the best ones we got? That's the natural complement to this. So the natural question that complements this one is, what about lower bounds? So to pose this question, it's very much like me asking, is there any algorithm that solves blank in little o of something time? Or you may even rephrase this and say, in at least big omega of a something time. These are a couple equivalent ways of saying the exact same thing. So, yeah. So do you see how you can use asymptotic notation to describe different things now? So now we're using big omega and little o to talk about lower bounds. Say at least. So in this sense, the little o is saying, can we do it in time strictly less than whatever's in this complexity function? Versus another way you could say the same thing is that I require at least this amount of time to solve the problem. So this is where we're going to be talking about things this lecture. So are there any questions about the overall game plan? So I've talked about upper bounds. Now I'm going to be showing you some techniques for establishing lower bounds so that you can get some idea of like, okay, so if I have a problem, like is there like a giant gap in our knowledge about the most efficient algorithms we have versus like our theoretic lower bounds on like, is there any way we can improve our algorithms? So if somebody comes along to you and says, hey, can I solve this problem in big O of this time or something like that? And you could point to them and say, hey, look, no, you can't do that, at least under this assumption or this assumption. This is something that's rather handy, especially if you're looking at different common problems that you might run into and somebody asks you a natural question, can we do it faster? So this is this is me giving you an introduction to how we can address this. So if we're okay with this, give me 2 thumbs up. Wonderful, wonderful, sweet. So now I'm going to shift gears. Let's start talking about searching. We're going to talk about searching first. So I'm going to introduce you to a technique. So searching and introduction to adversarial arguments. So I'm going to be introducing you to an interesting but oddly abstract idea that will allow us to effectively come up with these lower bounds. Sometimes certain lower bounds techniques are helpful for getting certain bounds. Other ones are too weak to establish certain results. So I'm going to be trying to show you a few different ways you can to come up with lower bounds. So first we're going to consider the search problem. And I want to determine a lower bound for this. So we're going to consider any unsorted array. So I'm just going to assume the array has any arbitrary order to it. And I want to determine how, is there any required number of operations that I need to perform to solve the search problem. So, and one thing I want to really be clear about is when we do this, so I want you to remember this. This is a very important fact in these types of arguments. Because remember, we're trying to establish a lower bound on how efficiently we can solve a problem. We cannot assume any one algorithm, okay? Any one algorithm. The result we prove must be true for any algorithm that solves the problem. So that's the common pitfall that I often students run into this kind of stuff, is you find yourself trying to establish a lower bound, but you start assuming that there is a certain algorithm, and that's what you don't want to do. Because remember, we're trying to establish how many operations are required at least to solve the problem. Now, you could talk about all sorts of bounds that you can derive through some algorithms, but most certainly if you want to develop absolute results, you can't make any one assumption about what the algorithm does. So this is where I'm going to bring in our best friend, the adversary. So let me go get my adversary. I'm going to go get my adversary. Okay. So here's my adversary here. Here we go. There's my adversary. I got out of his swamp, okay? So anyways, so what we're going to do is we're going to talk about this concept of an adversary. It's at first it sounds very abstract, but so if you find yourself just having a hard time attaching it to something, think of this lovely character here. So let's talk about what an adversary is. I'm going to frame it in terms of the search problem, and then you're going to see that I'm going to really talk about it more like we're playing a game with the adversary. So I'm going to give you the idea of the adversary. And I must stress that depending on what kind of problems you're studying, you might even change the rules on certain assumptions that the adversary can make. So for example, some adversaries, at least if you get into some more advanced theory stuff, sometimes people make assumptions about the omniscience of the adversary. So for example, they might say, oh yeah, the adversary can know everything that happens with the execution of your algorithm. Some people might have maybe the adversary may only know a certain number of bits of the input. Things of this nature are quite common to assume for the adversary. For us, we're just going to take the most simplest kind of adversary we can have, okay? Or at least the way I'll present it to you. So I'm going to keep this somewhat informal at first. First, we present the concept of an adversary. As a guessing game. So we're going to be thinking of this like a guessing game first, and then I'm going to try to explain it once we get to the meat and potatoes of this idea, how it ends up getting used for developing a lower bound, okay? So we're going to think about this like a guessing game. So I want to first suppose you have some algorithm that asks questions. You can think of these as guesses about the input. About the input. Now remember, I'm saying some algorithm. I'm not saying any one particular one. I'm just saying that you give me some algorithm. And so just to reiterate, suppose you have some algorithm that asks questions about the input. Now, we're going to assume our adversary has maybe not our best intentions in mind, but will lead us and steer us the way out of the swamp, okay? So what we're going to do is, imagine we trust this adversary, and we keep asking questions to the adversary. We're going to assume that this adversary may be potentially malicious. As in, every time I make a guess, the adversary is just going to try to keep me asking as many questions as I possibly can. Just like if my lovely adversary here took me on a trip to get out of the swamp, it might take me the longest route possible to get out of the swamp. If I keep asking, do we go left or do we go right? So, and the whole idea here is that I'm going to make no assumptions about what this algorithm exactly is going to do. Instead, it's going to be about what the adversary is capable of throwing at me to cause the algorithm to take as long as possible. So imagine, that says imagine, the E sort of melted there. Imagine some malicious adversary that can craft for each question a worst possible answer. I'll write it above here. A worst possible answer. So the one thing that I need to be clear about is as these pieces that the adversary is going to craft are being made, at least remember, I got to keep this rather abstract. When you see it come together in the proof, you're going to see that I'm going to give you very constructive things. So what's going to happen is this adversary is going to cook up an instance, regardless of what the algorithm does, that's going to cause it to perform as many wrong answers while still constructing an instance that is valid to solve the problem. Just like when I talked about my lovely adversary here. This lovely adversary, I'm asking the adversary to help me get out of the swamp of this nondescript character. I keep asking questions, but the adversary in this case, my friend over here, can come up with a pathway already in mind that whenever I ask a question, the adversary can send me in the direction that takes me the longest possible to get out of the swamp. So you're going to see how this is going to play out in a moment. So I got one other point I want to make about this. I know that this sounds really abstract at first, but I assure you, once you get over the hump of the game plan with this, it will click a little bit better. So if at first it sounds a little bit strange, it does usually. So let's head over here. I'm going to take my lovely adversary with me. Got to be gentle. So let's head on over this way. So, Yeah, I know, right? I know, right? So now, just to kind of summarize what I was saying, this sequence of malicious answers causes the algorithm to perform the most number of guesses leading the algorithm to the right guess. So like I said, this lovely character might lead me away out of the swamp, but might take me on an extra route all the way around, taking me on the longest route to maybe spook the heck out of me, so that I get out of the swamp but I don't come back. So the one thing I want to stress about the way the adversary crafts the instances is that it has to be consistent with one input. So it's not like my lovely adversary can make up any sequence of guesses. It has to be still something that resembles a problem instance that eventually has to look like one of the inputs for our problem. It must be consistent with one problem instance. So it's not entirely malicious in the sense that the adversary is going to still help us solve the problem. But most certainly, the idea here is that this adversary is an abstract construction that we're using to help us establish lower bounds. Yeah, it's kind of like lawful evil, yes. So this adversary doesn't actually exist. What this adversary actually is actually a way that we can think about building the problem instances, regardless of what the problem instance, what the algorithm is, so that it causes this to occur. So in our proofs, you're going to find that I'm going to present you some systematic way of describing an instance to you that no matter what the algorithm is, it will tailor to those set of decisions and cause it to take at least a certain amount of time. And that's how actually an adversarial argument works, believe it or not. Now you might say, Dan, I don't really like talking about this character here. He's a little grumpy sometimes. There's a couple of natural ways that you could think about this. I'm going to draw out a couple of them. You may have heard of them before. So just here's the main idea. No matter how or which sequence of questions are performed, the adversary can build an instance. So that it requires as many guesses as required, as many guesses I already say requires. I'll say as possible. And as possible is what we like to make as big as possible. So our goal is to try to make one of these adversaries that tries to get the algorithm to take on any one instance that causes it to perform as many operations as possible. But here's the neat thing. The way I describe this to you, it sounds almost like I'm automatically generating for you worst case instances, doesn't it? So if I give you one algorithm, I'll tell you how to build a worst case instance. Does everybody see that? So that's actually what's happening when we look at my adversary here. So if I give you any algorithm, the algorithm will do blank. With that blank, I will take it and I will build an instance. And regardless of what that algorithm is, it has to do certain things to find the answer. So notice that I'm trying to get away from thinking about there just being one particular algorithm. Now I'm just going to put any algorithm in that box and try to get it so it causes the worst case behavior. So you might think of how exactly you can imagine this. Now, for those that don't really like my analogy with this lovely character here, a couple games you can think of are, say, for example, Battleship. You may also think of another memory-based game. I think it's called Mastermind, if my memory serves me correctly. It's called sometimes other things. So in Battleship, how many of you have ever played Battleship before? I'll explain it briefly. So it's a two-player game where you have two boards. They face against each other, and they have coordinates on them. And people can place ships on the lower parts of these folded boards at certain coordinates. And the way the game is played is people take guesses at certain coordinates, one player after the other. And if you place a ship in a coordinate that is shot at, you put a peg into the ship. And the whole idea is you got to sink all the ships. So there's a whole set of them. They arrange the ships on the boards. And you take turns at each other, but you don't know where the ships are on the opposing person's board. So in the context of an adversary, the way you could think about this is imagine I'm playing Battleship with this lovely character, and every single time I make a guess, they move the ship, and I don't know what they're doing with their ships on their side. They're moving around the ships on their side. So that every time I make a guess, they move the ship so that I have to take as many guesses before I get Battleship, okay? That's effectively what's happening. But here's the big important detail, is that even though the adversary seems like cheating in this analogy, seems like the adversary is cheating, at the end of the day, if you look at the board after each one of those guesses, you end up with a board with a bunch of guesses in it, right? The point is that I've crafted some instance, so with some omniscience, some future foresight, my adversary could figure out all possible guesses that I could have and place them on the board so it maximizes the number of guesses, regardless of what sequence of guesses I make in Battleship. So, does that help anybody thinking about, say, Battleship? I know that there's a lot of different ways you can think about this adversary idea. But those are the couple I can think of that are great. Mastermind, that's a game where you have a pattern that's hidden behind a guard. You can imagine that this adversary is tweaking around with the pegs, with the colors behind this hidden guard, and the player has to guess the sequence of colors on the opposing side. They're given some limited number of guesses. The goal in the case of the adversary is if the adversary knew what guesses you're going to make, they could figure out what a sequence would be to cause you to perform as many guesses as possible. Yeah, that's an interesting example. That's a more recent example. Talk about Wordle. Yeah. So we're going to use this idea of an adversary. And at first this looks a little abstract, but I assure you, once we kind of play around with it, it will feel a little bit more natural. But the big idea here is that for every algorithm A, for input size n, the idea is that there's going to be some input, regardless, where I get to have this problem instance selected, and the adversary gets to decide this, where it takes at least a certain number of operations. So let me just write that on the board over here. So we'll put my lovely adversary over here. My great rival. But yeah, I usually like to think of it like we're kind of doing worst case analysis, but it's like automatic. It's automated. So regardless of what the algorithm does, you know how to a way to craft the instances so that you always get one that's going to perform at least some number of operations. So let me just say this. In formal terms, so this is more of the formal look of an adversary. In formal terms, we will show that every algorithm A, that for, I'm going to insert the word for, my apologies. It's very unusual for me to have to do that. Show that for every algorithm A and input size n, there is some input of the problem of size n, and I must stress that this is selected by the adversary. I'll abbreviate adversary with ADV just for the sake of brevity, where A takes at least L operations, L of n operations. So you're going to find that when I give you the actual proof, you won't see an adversary kicking around. You won't like see me bringing up this character over here that I will not mention the name of for dramatic purposes. So this is going to be the big idea. So I'm going to show you an example of how I can craft one of these adversary arguments. So let's consider the search problem first. So given an unsorted array L of n elements, the search problem cannot be solved in little o of n time. So my stress, remember, that's little o over there. The search problem cannot be solved in little o of n time. So let's walk through how we do this. So I want to give you the idea. So just think of that suspicious character over there. I don't know what they're going to do. My point is that I give you some algorithm. And what does the search problem do? So the assumptions I'm going to make, so these are the only assumptions I'm going to make. So if somebody asks you about what the limitations of this proof are, I'm going to assume that the only things I know how to do are testing if elements are equal or not equal. Those are the assumptions I'm going to make, which seem rather fundamental, right? If we want to know if we found it or not, we need those, right? So these are they're not very limiting assumptions. So here we go. And I'm hoping you could see where the adversary kind of fits in. And I'll explicitly show you where. Suppose algorithm A solves the search problem. The order the order A examines elements is, I'm going to give them names. I'll call them I sub 0, I sub 1, I sub 2, all the way up to I sub n minus 1. So what I'm going to do is I'm going to suppose I'm given an algorithm that solves the search problem, and the order in which it examines the elements is this. I sub 0, I sub 1, I sub 2, all the way up to I sub n minus 1. They could be any sequence of them. I'm just assuming that there's n of them there. But remember, if you made more guesses, they're just going to be duplicates. So I haven't made any wild assumptions yet, right? So remember, I'm not assuming any one algorithm when I do this. So far, we're doing okay. So I'm just assuming I have some algorithm, and I'm gonna sure it solves the search problem, and I'm gonna look at the order that I'm given these elements. And this is the order I'm giving them. These are just names I'm giving them. So watch this, watch this. So now this is where the adversary comes in. So the adversary's job is just to build an instance. So construct. So let's construct. And now this is where the adversary comes in. As an adversary could construct, as an adversary could. I'm putting that in parentheses because it's not required for the proof. It's just that it's very helpful to realize that we're dealing with an adversarial argument. As an adversary could construct array L so that, now if I give you all these positions, right? I don't know what they are, right? Now, those are just some numbers. They're positions that I'm examining in the array, right? Now, can anybody think of a way that I were to put those indices into certain spots so that I try to get it so that I get as many comparisons as possible? So think of it like those are positions I can look at. And remember, this is the order in which they're getting examined. I'll give you a, let's walk a little bit through this so that L sub I 0, L sub I 1, L sub I 2, all the way up to L sub I n minus 2. Question. All of these, do I want any one of them to be the key X? No, right? Remember, we want to lead me the longest way through the swamp, okay? I want to make the most dickish game of Battleship. Okay, so here we go. So I'm going to make all of these. Are all not X. And I'm just going to make the last position L sub I n minus 1. I'm going to make this be equal to X. So now if I give you any one instance and I tell you that's the order in which that algorithm will examine elements, you can see right now that it doesn't matter which algorithm I give you, right? It's always going to go through all of those, not find anything. Then the final one is going to find X. Does everybody see that? So remember, the adversary is an abstract idea for me to come up with this instance. And remember, it's completely oblivious to what the algorithm is. All I know is it just examines elements, and that's the order it does it. So A examines n elements regardless. Therefore, at least, running out of space here, I'm just going to try to squeeze it in here. Therefore, at least, big omega of n comparisons are required. And that's the end of the proof. So just let me reiterate this. So A examines n elements regardless. Therefore, at least big omega n comparisons are required. So do you see how I'm almost playing a game against myself? That I came up with a very smart way that regardless of, actually it's not even that smart, this is a rather oblivious thing to do. But it most certainly is enough that if I told you what order of guesses I make, in this case the examinations of positions, I can always show you that there exists one instance that causes it to perform some number of examinations, regardless of what the algorithm is. Isn't that kind of cool? So are there any questions about this? So notice that this completely strips out the idea that I know what the algorithm does, other than I know it just checks if they're equal or not. Are we okay with this? This is kind of neat. So we've given a way that we can argue about how much time we require to solve this problem. So if we're okay with this, can you give me 2 thumbs up if we're okay with this? Okay, great. So let's proceed. Now, for the purposes of time, what I'm going to do is I'm going to skip over the next example because it's another example of an adversarial argument. But it's one that I want you to take a look at. It's actually, I would argue, it's even simpler than the argument I presented here. It's actually based on a tournament. So let me just make a note of this. So you could actually prove that computing the maximum or minimum in an array actually requires linear time without any additional information. So you could actually prove, so I'm going to write another theorem for us. So given an unsorted array L of n elements, any algorithm that computes the max of L requires n minus 1 comparisons. So in short, it requires big omega of n time. That's awesome. So you might ask, where does this come from? Well, it's actually based on the idea that you look at each one of your elements in the array. So you imagine you give you an array, and you compare 2 elements. Suppose I give you like one that's x and another that's y, for example. I would like to know if x is less than y or x is greater than y. What you could do is you can have almost set up a tournament where we would say that if x is less than y, we get a loss for x, and if x is greater than y, then we get a win. Now suppose I give you one of these elements and it's say x. in the array. To figure out if X is the champion in the tournament, how many other elements are there? There's n minus 1 other ones, right? So this is actually how the basis of the adversary argument works. So I'll encourage you to take a look at the proof in the notes. But it's a nice little example of an adversarial argument as well. So the proof's just in the notes. But yeah, it's all based around the idea of a tournament. So just to remind you, so just the number of losers is n minus 1 in this case, and the champion would be the last one. But you can take a look in the proof if you want to look at some more details for another example of an adversary. It's a very neat idea, regardless. Now, another technique I want to talk about, so that's the first technique for lower bounds I wanted to talk about. Believe it or not. There's a second technique I want to talk about. This is one that I know you'll get to use on your second assignment. It's arguably simpler than using an adversarial argument. So I'll refer to it as lower bounds via reduction. So this is like the second technique I'm going to show you. I'm actually going to not talk a whole lot about it because it's really simple. But the idea behind what we're going to refer to as a reduction is a very powerful one we'll talk about a lot towards the end of this course. It's one of those tools that I wish students would be able to see earlier on in their program. It's that important. So here's the idea. Suppose you have two problems. Pi 1, so I'm going to call it capital Pi 1 and capital Pi 2. So imagine you want to prove a lower bound for Pi 1. So I would like, sorry, for Pi 2. I was getting a little ahead of myself. For Pi 2. That's going to be our goal, is to get a lower bound for Pi 2. So, if we can use if you can use Pi 2 to solve Pi 1, you may be able to, if you have a lower bound result for Pi 1. So here's the idea. It's actually not that complicated. So suppose you have a given problem and you want to establish a lower bound for it. Now, suppose you have a different problem where you know a lower bound result for it already. If you can use the problem that we're interested in, that we want to find a lower bound for, to help us solve the problem with the known lower bound, and you can tell me how long that takes, then most certainly this algorithm couldn't exist if I can use this one problem to help me solve the other problem. You most certainly couldn't solve the bigger problem with the smaller problem if you knew that the bigger problem can't be solved within a certain time. So the idea behind this is that we assume that there exists a faster algorithm that most certainly can't exist because it would allow us to solve Pi 1 faster. So let me draw you a picture to help explain this idea. So let me just move on over this way. So I'm going to present you an example involving sorting. So we're going to try proving a lower bound for sorting. So I'm going to refer to this, as I said previously, this is pi 2. So we're going to try to establish that we can't sort in time less than linear time. So I'm going to draw a picture here. So I'm going to say, suppose we have a little o of n sorting algorithm. So suppose we have one of these. And I don't know, let's call it, tempted to give it a name. Well, what we'll do is we'll say that this box represents sorting. And I'm going to try to use, if I know that this algorithm exists, to solve another problem that I have a known lower bound for. And if I can do it faster, then most certainly this algorithm, this one in this box, so this is my sorting algorithm, the one that I've assumed exists. So this is my little o of n time algorithm. So suppose I give you a different problem. Suppose, so I'm going to consider computing the max. So we're going to call that pi 1. So suppose I want to solve pi 1. So I have pi 1 here. This is computing the maximum. So computing the max. So let's come up with an algorithm that we can use to solve computing the maximum in little o of n time under this assumption. So I have an idea. What we're going to do is I'm going to take this and I'm going to feed this as, so if I give you an instance, say called x, so suppose x is an instance of pi 1, I'm going to give that over to my sorting algorithm, and it's going to sort that. So it's going to sort the array, and then I end up with a solution. Actually, let's put it in here. Let's draw a little box here. So this puts out a sorted array, right? Right, that's what the sorting algorithm will do. Because you'd agree with the computing the maximum, that problem instance is just an array, right? So it outputs the sorted array. Now, if I have a sorted array, how can I compute the maximum in that array? It's the last element, exactly. Exactly. So if it's sorted from smallest to largest, well, what you could do is you could just return the last element. However, if you look at this picture I just drew here, I just gave you an algorithm for computing the maximum. But what's the time complexity of this? Well, I give it to the sorting algorithm. I end up with a sorted array. And then I just return the last element. So how long does this algorithm take? In terms of little o. So keep in mind. So I take the instance, I sort it in little o of n time, and then I just return the last position. Now remember, little o just simply means it's some running time that is less than linear. Yeah, it's little o of n. So this whole thing is a little o of n time algorithm. Sorry, my writing's a little strange today. Little o of n time algorithm for pi 1, right? Why? Because it sorts it, and then you select the last position because that simply is the largest element. But what's the problem with this, everybody? What's the problem with my assumption? What's the problem? What did I just tell you earlier? There's a problem with this assumption that I made over there, right? Can I actually, so if I had this algorithm at my disposal, yes, exactly. So there is no sorting algorithm that could do it in sublinear time. So little o of n would mean sublinear, better than linear. Correct. So we cannot sort in little o of n time. In fact, the way you would craft this as a proof is using contradiction. You would assume that you have this algorithm. And then what you do is you just simply go through the process I did with my picture. But you just write it in words. You just say, okay, well, the input of computing the maximum is an array. I give it to this sorting algorithm. It sorts it. And keep in mind, it does it in little o of n time. And then I simply return the last position. And this is the maximum. So the overall running time of this algorithm is little o of n. But I just presented to you an algorithm that computes the maximum in sublinear time, right? That's not possible. I just gave you that as a theorem just a moment ago, right? So this is actually just a contradiction proof in disguise. So the whole idea with the reduction here is that pi 2 helps us solve pi 1. So if there's some way I can use pi 2 to help me solve pi 1, and if I make the assumption that this algorithm's way too fast, like I mean it's so fast that it actually doesn't exist, the whole idea is that I have assumed this box exists here. The contradiction is that this box actually doesn't exist, which is really weird to think about, right? It's weird. It's strange, right? I've assumed the existence of an algorithm that doesn't, after you walk through the steps, it can't exist. Isn't that weird? It's kind of weird, right? But yeah, no, so using this, we can establish that there is no algorithm that sorts in little o of n time, aka it requires big omega of n time to sort. Now, you might ask, yes, it's kind of like that. It's a fun box here, but the box doesn't actually exist. It's for the purposes of a contradiction proof. So when you do these types of reduction proofs, all you do is imagine you had an algorithm that can run faster. And then what you do is you use that to help you solve a problem that you know can't be solved any faster. And the contradiction comes from, you give me the algorithm under this assumption, and you say, hey, look, I get you a faster one, but you know that doesn't exist. Contradiction. So anyways, with that being said, when we come back, we'll talk, actually, one thing I want to stress is that in the notes I talk a little bit more about how you might phrase this in words. But when we come back, I'm going to show you one more lower bounds technique. It's easily one of the more interesting ones. It's actually the one that actually improves on this sorting lower bound. So this lower bound is for linear. It tells you that linear, you're not going to beat linear regardless, right? However, for certain cases, like our case where we have comparable elements, I'm going to show you that n log n time actually is the best running time. We'll do that next time, okay, everybody? So I say thank you very much, and have yourself a beautiful day. I'll see you later.